Nathan. Oh my gosh. Good morning, everybody. Oh, I have to sneeze, guys, and it's just stuck. Okay. Anyways, good morning. I just hung around our house for a while, and then one day he disappeared. Oh my gosh, what if he got hunted and you ended up having him for Thanksgiving? That would be really sad. Circle of life is not good to turkeys. And he wasn't one of the pardoned turkeys, like the president pardons turkeys, which I think is the weirdest tradition ever. Ever. Oh, anyways, I feel sorry for people who have to rewatch the recordings because they're probably like, what are they doing in class? Anywho, welcome back to another episode of Chemistry with Miss Stanley. All right. Today, we are starting a new unit, everybody. Congratulations to each of you for making it through your first unit of chemistry. Before we get started and for the next 2 minutes, I'm going to kind of poll you all. Then I'm going to send out an official poll tomorrow morning once I create it about how you feel that first unit went. Did you like having the mastery checks? You can just let me know in the chat, yes or no. Did you like having the mastery checks in general? You can let me know yes or no in the Chiznat. So that was the option for me as a teacher. Yeah, the option for me as a teacher was either give you guys this 45 question test or kind of break it up into mastery checks with the learning targets. So I wanted to see how you guys felt about them. Oh, never mind. I like them. Oh, okay, Layla. Okay, okay, okay. Jacobs, yes. And guys, it is socially acceptable to say no. Like this is. I hope you guys do understand that. Like, we are a fun-loving environment, so you can disagree. You can be the only one who says like it's not that deep. I just want to poll everybody to make sure. Another reason why I, as the teacher, like them because you guys really participated with them. Like your participation rate was really up there. Yeah, the test, I know. Yeah, it's kind of like a unhappy medium, Layla. But if there is something that you do like, Layla, like if there's like a type of assessment that you prefer, just let me know because we can work it into class. Like this is you all's class. However assess the best is how I want to assess you. So if you think of something that you prefer, let me know because we can work it in. Okay. So just shoot me a message or something if you figure something out. Because that's how this class works. But okay, so you guys overall like them generally. There's some things we can work out. The next thing is, which is something you guys can decide as a class. So your notes for this class have been an assignment. So you've gotten points for them. You've gotten credit for doing your notes. However, it doubles the amount of assignments in Schoology that you have. So for each learning target, you had notes and a mastery check. So we had 5 learning targets last unit, which means you had 10 total assignments, which was overwhelming if you got behind. So as a class, do you feel like we should not have the notes as an assignment and just have them as like, I don't know, I'd have to figure that out, but I think it's possible. And just have them kind of as like a page on there where you can still take notes, but it won't show up on your Schoology as something you have to get done, or keep them as an assignment. Okay, okay. So just let me know, like, do you want to keep them as an assignment so that you can see them on the side of your page, or did that stress anybody out? Let's see how we're feeling. because I think if you don't keep like if you don't keep up in this class, like if you don't um come to class and participate, it probably stresses you out. Okay, good. I don't like it at all because I only take notes if there's something I know I won't remember. Okay, that makes sense. Gail, I don't mind it. Keep them. Okay, okay, okay. That makes sense. Exactly. That's what I was going for, Haley. That was like in the teacher in me. That was my objective. Because I feel like you guys need easy 100s every now and again. You know what I'm saying? Um, and Kale, now that makes sense too. So we're gonna work that out. We'll talk in our tribal council about what to do for you, Kale, to make it work for you because I just want what's best for you guys. Okay, good chat. Thanks for letting me know. We'll talk a little bit more in depth tomorrow, but I just wanted to get an overall vibe. Sounds like it's, pretty straightforward. Okay. Let me know if there's something in another class that you prefer over what we do. Just keep me in touch, okay? Because this is you all's class. Apollo. Yeah, everybody did. It's okay, Nathan. There are no dumb science questions. They're just science questions. It's okay. Everybody bombed the pretest. So that means we all get to have a great starting point. Okay. Physics is technically Ooh. I've had this. Okay, that's funny because I've had this heated argument in one of my grad school classes, and I voted yes, but nobody agreed with me. So maybe I don't know what I'm talking about. So we'll delve into that. I like that. I'll go back in my notes and see what they decided. Um, okay, let's get these notes done so that we can go back. All right. You should have 4.2.6 opened. 4.2.6 means we are in week 4. We are in unit 2, learning target 6. So go ahead and open this up. It should be a cute little PowerPoint there. And you should have taken your pretest, which is fine if you didn't do well on it because that's what today is for. Okay? All right, here is our learning target. I can describe the current atomic model. And we're going to talk about how we got there. So let's see. You took your pretest, right? Everybody take this? Everybody take their pretest? I'm assuming yes. 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 Good. 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 It's okay if you didn't do well. That's what pretests are for. Awesome sauce. All right. Here we go. It's okay. That's what pretests are for. All right. So the first guy we're going to talk about is Democritus. All right. This guy discovered that if you cut something in half, at some point, you can no longer cut it in half because it will be so tiny, right? So, like if I cut, a piece of paper in half, and I cut that half in half, and I cut that half in half, and I cut that half in half, and keep cutting, keep cutting, keep cutting, blah, 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 blah. At some point, I'm going to get a piece that is going to be too small to cut. And that uncuttable particle is called an atom. He called it a atom, but we call it an atom. Okay? So he was like, at some point, this has got to happen. And so this what ends up happening. He named this uncuttable particle an atom. Okay? An atom. I'm dropping these in the chat if you need them. All right. My document isn't loading. Uh-oh. Steven, in the meantime, in between time, is anybody else having trouble loading your document? Let me know in the chat. In the meantime, if you just want to write down the underlined words like on a Word document, you can. In the meantime, or a Google Doc. Okay. All right. So what happened after Democritus? Well, we discovered that oh, of course it is, because hashtag virtual school. We discovered there's something called an atom, and there's this thing called an element. An element is a pure substance that can't be separated into simpler substances. And those substances are atoms, right? And it's only made up of one kind of atom. Okay. So elements, we've already talked about this, but it's like a single solitary type of atom. There's nothing else with it. It's just oxygen. It's just potassium. There's nothing else with it. Okay. The atom is the smallest particle in which an element can be divided into and still be the same substance. So if I keep chopping an element up, the smallest part is going to be the atom. Okay. And of course, atoms make up elements. I'm sorry, that was really quick. All right, so these are basically your foundational words. All right, everybody. These are critical because it's like your whole life. You've heard of the periodic table of elements. So like, what is an element, right? Now you know. Okay, lots of words to fill in here. So I'll wait on 3 of you guys to let me know, 4 of you all to let me know you are finished. Just give me a thumbs up in the chat when you have filled in all your words. Finished. 1 person finished. Waiting on 3 more. My glasses are so dirty. Let me know. 2 people are finished. Waiting on 2 more. Whoa. Okay, I'm just gonna keep moving. All right. Oh, 3rd person. Good. Thank you, Steven. All right, next slide. This slide is already in the chat. This is me stalling. Okay, great. All right. The next guy. Thank you, Kale. The next guy, John Dalton. He's a pretty big deal. I'm not gonna lie to you. He's a pretty big deal because he came up with these 3 postulates, right? His important details is that all matter, so that's, matter is anything that has a mass and takes up space, is made of atoms. Okay. The atoms are indivisible. We already knew that because Democritus told us. But he added another word, that they're indestructible. That indestructible part gives way to another theory that's going to come around in about 100 years from where we are right now in the timeline. Okay, so he discovered they were indestructible. Now, the second thing he came up with was that all atoms of a given element are identical in mass and properties. So his thing was, which gets disproven later on, is that an atom of oxygen is going to weigh the same as another atom of oxygen. Like I just said, that's going to end up turning out to be false, and you'll see why. Atoms join with other atoms to make new substances. Well, that makes sense because you have H2O, which is hydrogen atoms and oxygen atoms joining together to become a great big force called dihydrogen monoxide, also known as water. Bam, bam, bam. So yes, John Dalton was really, really important. Shout out to him. Pretty cool guy. Never met him, but We appreciate him. All right. Moving forward. Stop me if I need to slow down. Okay. Oh, there's more here. So atoms are hard and dense like billiard balls, like pool balls. Okay, so that's what he came up with. He was like, so at the end of the day, when you break everything down, they've got to become this very dense particle, which is an atom. Now, Yusuf, yay! Good morning. Good morning, Yusuf. Good morning. Now this proved to be false, right? Because let's be real, that's not actually what's going on. There is a dense portion of an atom, but it's not the whole atom. So the modern atomic theory is gonna explain more of Dalton's theory, but Dalton, Dalton's theory became the foundation of chemistry. So without him, there would be no me teaching you. Thanks, Dalton. We appreciate you. So yes, he became the theoretical foundation in chemistry. And we'll talk about more about isotopes next week. Okay, I'm gonna put a better picture in the chat for you now. There you go. All right. Any thoughts, questions, or confusions? I'm gonna keep going forward. All right, J.J. Thompson. You know, this guy was pretty cool. He discovered the electron, right? He realized that the accepted model of the atom did not account for negatively or positively charged particles. So what does that mean? So remember when cool Dalton guy, he was like, yo, it's like a billiard ball and it's like a circle. And I was like, cool. But when Thompson was like experimenting and whatnot, he realized that some part of it were positive and some parts of it were negative. So at some point, somebody got to account for this. And that's where we came up with the electron. Okay. It has this modding called the plum pudding model. Why it's called plum pudding? Great question. So it's called plum pudding because assumedly plum pudding has like plums in it, I'm assuming. And I'm assuming the plums are like noticeable in the pudding. I prefer to call it banana pudding because you know, like sometimes with banana pudding, you can have bananas in it, like actual banana slices in the pudding. So that's what I call it, but fancy people call it the plum pudding model. Um, so the problem with his plum pudding model is that he discovered the electron, which is negative, but he didn't really quite figure out what was going on with the positive portion of the atom, which makes sense because of what somebody else is about to figure out. Okay, so J.J. Thompson discovered this plum pudding model. Plum pudding model. So he took it from the billiard, which is like the pool ball, and created this plum pudding model. Okay. All right. Moving forward. Okay. So how did he discover this? Well, he used this thing called a words I can't say, ray tube experiment. We're gonna watch this experiment. You can click this link on your page. I think it might just be a URL that you have to click. But watch this video. It is 2 minutes and 50 seconds. Let me know in the chat when you have finished watching it. So go ahead and press play on this video and let me know in the chat when you have finished watching it. Right. There should be audio on yours, not from the one I'm playing on my screen. Also, don't have any audio. Awesome, 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 awesome. It looks like you guys are finishing up with this video. So we have this new thing called an electron that's been discovered, right? It's negatively charged. And this ray tube experiment helped us figure that out. Now let's see what else happened in history. Good old Rutherford. Rutherford was an interesting fellow. The way he's interesting and why he's interesting is because he had this really cool experiment called the gold foil experiment. All right. So this helped us discover that the mass, like the weight of the atom, was concentrated in the nucleus. Okay. And therefore we end up with the nuclear model of the atom. All right. So what does that mean? Remember when old dude was like, and by old dude, I mean Dalton, he was like, "Oh, it's a billiard ball, right? Like it's a pool ball. You know how like pool balls are heavy and if you throw them, they hurt, right? Don't throw pool balls." But the reason why he came with that was because he knew that there was mass related with it. He knew it was probably a circle, but he didn't know where that mass was concentrated. And so Rutherford used the gold foil experiment to figure out that, oh, the mass is in this thing called a nucleus, and the nucleus is the center. So the majority of the mass of the atom is going to be in the center. And this is when we came up with the nuclear model of the atom, where we put the mass in the center and we have things around it. However, He didn't quite know that there is this thing called a neutron. Cute little Chadwick figured that out later on. Now, here's the funny part. So, Rutherford was Thomson's student. And so, Thompson's plum pudding model was disproved by Rutherford. So, in this case, the student expanded upon his teacher's knowledge, which is what you should do as a student. Always take things one step further. Okay. So remember the plum pudding model? This is what I want to make clear. This plum pudding model, remember the bananas are everywhere. The plums are everywhere in the model, which is not accurate because by the time we get to the nuclear model, we recognize that the mass of the atom is in the center, not everywhere. It's just concentrated in the center. All right, let's keep it pushing. Here is a gold foil experiment. So go and watch this. We are not watching the whole thing. I'm just going to tell you about it. So what ended up happening with this gold foil experiment? He shot some, like this right here. I'm just going to tell you about it. So he shot some like, how can I explain that? He shot some rays at a piece of gold foil. What ended up happening is, if you look on this next slide, some particles went straight through. Can you put a screen? Ooh, I can. Thank you, Nathan. Sorry about that. Thank you for telling me. Boom. There you go. Thank you, bud. All right. So what ended up happening is he has this, you're welcome. He has this radioactive source and he shoots alpha particles and beta particles at a piece of gold foil, literally a piece of gold foil. And what ended up happening is some of the alpha particles came back. Some of them came back. Some of them went straight through. And then others of them went different directions. So some went straight through, and it was like as if the gold foil wasn't even there. Some of them went sideways, and so they were deflected at small angles. And some of the alpha particles came back. So what happened? Well, the ones that went straight through, that proved that the atom is mostly empty space because they went straight through the gold foil. All right. The parts that went off to the side, that proved that the nucleus was positively charged, as is the alpha particle. Because when two positive things meet each other, they're going to go opposite directions. So they'll go off to the side. Now, sometimes the alpha particle came back. Now, this is because the nucleus carries most of the mass of the substance, okay? The whole point is that alpha particles are positively charged. And we're about to figure out exactly what these positively charged particles are, okay? I don't think you had anything to fill in on this slide. All right, well, shout out to Bohr. Bohr comes around. He's a pretty cool guy. We'll be saying his name a lot because he's not boring. All right. Bohr discovered the electron shell model. All right. So we finally got the idea that the center is where most of the mass is, and that center is positively charged. All right. Well, what happens to those negatively charged electrons that we discovered way back when? Well, they go into this thing called an electron shell model. All right. This is the concept that electrons revolve around the nucleus at certain distances. The distances are exact. They're not just like roaming around randomly. There is actually an order and a sequencing to it. Okay. So he came up with the electron shell model. We'll be using the Bohr model a lot, even though it was expanded upon. Okay, these different series represent distances between different levels, okay? So this one, the Lyman series, starts from n equals 1, or the energy level that's closest to the nucleus, okay? And it's the distance from that level to the different levels. The Balmer series starts at the second energy level, and it's the distance from the second to the third, second to the fourth, second to the fifth, second to the sixth. And the Passion series goes for the third energy level. You will not be responsible for this. I just wanted to expose you to it before you leave my class. Okay? All right. Then we end up with this guy named Schrodinger. I don't know. I call him Erwin because that's a more fun name anyways. Erwin. All right. So he was like, this is all cool and theoretical, but let's throw some math in there, which is, of course, what chemistry is, right? So he threw the math in there that there is an exact distribution of electrons in an atom. That's called the electron cloud model. But then he was like, what about the probability of electrons are in a 3D model instead of the Bohr model, which is like flat on a piece of paper? So what if they're not going just in one dimension? What if they're going in a 3D dimension and they're moving like so? And that expanded upon and became the electron cloud model, okay? Which is more accepted because things aren't moving in just a circle manner. That's why the world is not flat. All right. That one is in the chat. So what else happened? Well, Heisenberg was like, oh, well, that just means that you can't exactly pinpoint where an electron is. And he was like, for sure. So that's why it's called the uncertainty principle. The uncertainty principle means that we are not certain about exactly where an electron is at any given time. That means we don't know where an electron is at any given time. We can guess, we can assume, but you can never say exactly where an electron is for more than like a nanosecond. Because remember, things are constantly moving and electrons are constantly moving. So you can mathematically work them, but you will always be working with an error of probability. That is called the uncertainty principle. Okay? Shout out to Heisenberg. Appreciate you. Anybody? Everybody good? I dropped this one in the chat already. Okay. So what about the models? All right. So the models are created to help us explain what is scientifically going on. All right. So let's think about this again. We started out with the pool ball, right? He's not on here, but we started out with the pool ball. We knew it was some kind of circle. And then we went to the plum pudding model, where we knew there were positively and negatively. Well, he just knew there were negatively charged things. But we knew that some kind of charged particles were involved. And then we moved to the Rutherford model, where there's actually a dense circle. There's a, well, not necessarily a circle, well, it is a circle, but there's a dense circle center to an atom, okay? So then we moved to the Rutherford model, where the electrons are just moving around the nucleus, okay? They're just moving. There's no exact science to it. They're just moving. And then we have the Bohr model, and the Bohr model is where there are different energy levels, and so it kind of categorizes what spin we're going into. But the Bohr model states that, you know, if an electron is going to be on that third energy level, it's going to be on that third energy level. Okay, but that's not always the case because there's the principle of uncertainty, which is why the Erwin model, or this name I can't say model, abandoned the idea of the precise orbits and the electrons just float around in this cloud type thing, which is the more accurate model. Okay? Why does this matter? Because it is matter. This is what is occurring around you all day long. Okay? So this is what chemistry is. We will be talking about the specifics of what are these particles floating around, what are the particles in the center, like what is going on. We're going to talk about those more specifically, okay? I don't think there's anything for you to have on this slide. So here's a cute little summary because we went through a lot, right? We had Dalton. Dude was like, yo, is something going on? But first, before him, we had Democritus, who was like, at some point, you can't cut this slice of bread any smaller. Like, even the crumb can be cut in half, but at some point, you can't cut that crumb in half anymore. So then Dalton came around and was like, okay, well, there's got to be something going on here. And Thompson was like, cathode ray experiment. There's some positive stuff and there's some negative stuff. All right. But we don't know about that positive stuff just yet. So we have this plum pudding model. Everybody just in the pudding together. Then Rutherford was like, hey, yo, teacher, I don't know how true that is because here's this gold foil experiment where some things are going through the gold foil, some things are going off to the side, some things are coming back at me. So that means that this center of this atom has to be positively charged. All right. And then we have Bohr, who took it a step further and was like, you're right. There is a positively charged center, but that means that there is a negatively charged outside. All right. So that's where the electrons are. And then we have Erwin. Erwin came in and was like, yeah, I know you said everything goes in a perfect circle around everything, but that's not necessarily true. We're not moving in a one dimension. We're moving on a 3-dimension. North, south, east, west. Okay. And then we come around. Yeah. Then we come around and it's like, what? I don't even know what's going on. So we have, because the electrons are negative, that's why they're going around the outside. And that's why the gold foil experiment worked, because the protons, boom, are in the center, right? That's why they came back. That's why they went through, and that's why they went off to the side. So close, so close. Neutrons are going to be neutral, which took forever for people to figure out, because if something is neutral, you can't hold a magnet to it and something happens. Yeah, you can't like force a neutral something to happen. So we got to figure out how they discovered a neutron. We'll come back to them. All right, so there's your theory. A theory is the explanation. A law is the description. All right, so the theory is why it happens. The law is what's going on. All right, just so you know, I'm not going to test you on that. I don't think it's on the quiz, but I don't remember. All right, theories don't become laws and laws do not become theory. That's important, just for your future references. All right, so we are going to now go on a scavenger hunt. So we learned about a bunch of historical figures who were great and did a lot of fun things for us. But what about some scientists of today and within the last 100 years? Well, let's figure out if we can find some cool ones, okay? So there's a Google Doc attached. There should be a hypothetically, there's a link there. There should be a link. Do you see a link? Yes. Do you see a link? Yo. Do you see a link on the page? It should be a link to a Google document. If you do not see said link, I will drop it in the chat. Ooh, this thing has a migraine. All right, so there you go. It's in the chat as well. And it should look something like this. Do you see it? Do you see it? Yay! Everybody's here. All right, so this is what you're going to do. You're going to claim a scientist, all right? So if you claim a scientist, put your name in the researcher's name box. You only have to claim one, so you don't have to be a super duper duper star. Go ahead and claim it. First person to get their name typed in the box is claiming that person, all right? Your job is to fill in these boxes. It should take you less than 8 minutes, but I'm going to give you 8 minutes. Your job is to fill in the boxes. Make sure you get me a cute little picture of it, picture of the person and their contribution to science, and paste the link where you got your information to in the sources column, and give me their dates of life. If they're still alive, just put a dash because they're not dead. Okay? Go be great. Here's your timer. You have 7 minutes and 30 seconds. That timer doesn't work. Neither does that one. Okay. That timer doesn't work. 8-minute timer. Ooh, lots of noise. Everybody is claiming a scientist. There are literally 5,000. Literally a bunch of them. Use the googly wooglies to help you. We'll do 6 minutes and 30 seconds. Jack be nimble, Jack be quick, Jack jump off the hickory stick. Oh, I don't think those are the words. My call keeps dropping. I missed what you said. Okay, it's okay, James. What we're doing is click the link right above the comment you just commented, and pick a scientist. All right. So your job is to find their date of life, what they contributed to science. So tell me like their most famous thing. Don't give me anything like general, but give me like what are they famous for? Like did they discover the proton? Did they discover a blood bank? That kind of stuff. And then you're gonna paste a picture of them that you find from the interwebs, and then you're going to paste your sources. Okay. So you can claim whomever, and do it that way. Okay. Dickory, dickory, found a clock. Whoa, 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 whoa. Guess what I should be doing right now? Taking attendance. Today's Tuesday. Pretty sure everybody here right now is also here on Friday. You said Layla, Eva, Michael, Jacob, Trinity, Christian, Lexi, Connor, Kale, James, Haley, Jenny Sullivan, Steven, good morning, Jenny. Alrighty. You guys are doing great. I don't even think you're gonna need all this time. My guy died on. Oh, did he actually die, or was it an April Fool's joke? Dark humor. Wow. Dark humor. Oh, what's our timer? 5 minutes. Keep going. Keep going. Keep going. Keep going. 1950. That wasn't even that long ago. Can you believe that that really was actually that long ago? That was 70 years ago. To me, I still feel like 1950 is only 50 years ago. It's just me. Where is my timer and why won't it work? You guys are doing great. Y'all's attendance is fantastic, seeing as we meet at 7 o'clock in the morning. That is really good, guys. Really good. Really, really, really good. This is looking great. This is looking great. This is looking great. It's basically just have it. You know what? It is possible. So, James, if you want to paste your info in the chat, I can grab it and put it in for you. That is definitely possible. So, your call. I do not mind helping you out. 2 minutes and 30 seconds. No. Y'all encourage me to make me cry. Hopefully so. Hopefully so. Y'all are killing the game. What? 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 I wonder who the coolest scientist. I mean, they're all pretty cool. What's the Manhattan Project? Sorry, I know I'm probably creeping you out as I read these things. Plants? What? cool that is? I'm learning way too much. This is too much. Yes. Color portraits. Yes. Do you guys need longer than 90 seconds? Yes, statue. Simple it. Thank you. Torricelli, yes, or is it Torricelli? I think it's Torricelli. Torricelli. What about Alma? Good job, Trinity. Chemotherapy? He came up with chemotherapy? What? Ah, interesting. Leprosy? I'm learning so much, guys. We're gonna have to figure out something cool to do with this information. But we'll do that in 9 seconds. Anybody need longer than 9 seconds? Looks pretty good. Looks pretty good. Looks pretty good. I think everybody's almost finished. 0 seconds. You guys may need a little bit more time. Oh, hello, fresh. All right, few more seconds. I think we're finished mostly. Good work, everybody. Ernest, good old Ernest. All right, so we're gonna do something cool with that. What that cool thing is, I don't know yet because the rest of them have to be completed with my other classes. So we will journey into that. Next thing I want you guys to do is to go ahead and finish and do this mastery check. So let's submit this PowerPoint. Everybody know about him. You know what I'm saying? Everybody know George Washington Carver. You know, he created my second favorite food, peanut butter. Everybody know about him, you know? So that's why I skipped him. I was like, everybody know about George Washington Carver. Let's learn about some people that Miss Stanley don't even know about. Right? You know what I'm saying? Trying to keep it hip and fresh. The shizzle. So let's go ahead, press submit on this. Press submit, press submit, 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 submit. Turn these in, turn these in. Turn in these documents for me. Kale's notes. Good. You did Albert Einstein. Okay, I will add that to our list. Where is the document? I just saw it. Okay. All right, so go ahead and submit these notes. So I built in some error in the form, Nathan. So it's not going to force you to be exactly correct, but just don't misspell words because I didn't build in like misspelling of words, if that makes sense. Like don't spell plum PULM, like try to spell it right. Yes. I'm gonna stop this recording.